Assalamualaikum and hi everyone. I'm Farahim. I'm gonna explain about contiguous memory allocation, which is the part of memory management. The main memory must accommodate both the operating system and the various user processes. We therefore need to allocate main memory in the most efficient way possible. The memory is usually divided into two partitions, one for the resident operating system and one for the user processes. We can place the operating system in either low memory or high memory. The major factor affecting this decision is the location of the interrupt vector. Since the interrupt vector is often in low memory, programmers usually place the operating system in low memory as well. We usually want several user processes to reside in memory at the same time. We therefore need to consider how to allocate available memory to the processes that are in the input queue waiting to be brought into memory. In contiguous memory allocation, each process is contained in a single contiguous section of memory.
Assalamualaikum warahmatullahi taala wabarakatuh. I am Nuruzatul Hidayah binti Mustafa. Would like to discuss the issue of mind mapping and protection. We can provide these features by using a relocation register and limit register. With relocation and limit registers, each logical address must be less than the limit register. The mind mapping unit maps the logical address dynamically by adding the value in the relocation register. This map address is sent to memory, as you can see at the figure. When the CPU scheduler selects a process for execution, the dispatcher loads the relocation and limit registers with the correct values as part of the context switch. The relocation register schemes provides an effective way to allow the operating system size to change dynamically. This flexibility is usable in many situations. For example, the operating system contains code and buffer space for device driver. If a driver or the operating system service is not commonly used, we do not want to keep the code and data in memory. Such code is sometimes called transient as code. It comes and goes as needed. Thus, using this code, change the size of the operating system during program executions.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurazah binti Yamadi. Now, I will describe about memory allocation. There are two methods that we can use to allocating memory, which is fixed size partition method and variable size partition method. First, let me see about fixed size partition method. From this method, memory will divide into several sizes of partition. Each partition may contain exactly one process. Thus, the degree of multi-programming is bound by the number of partitions.
In this multiple partition method, when a partition is free, a process is selected from the input queue, then is loaded into the free partition. For example, this job 2 is located here and job 3 is here. Then, when the process terminates, the partition becomes available for another process. For example, this job 1 is terminated, so job 4 is available at this frame. This method was originally used by the IBM operating system or 360 operating system called multiprogramming with a fixed number of tasks, MFT.
Next, let's see about variable partition method. In this method, the operating system keeps indicating which parts of memory are available and which are occupied. Initially, all memory is available for user processes and is considered one large block of available memory which is a whole.
In this example of dynamic partition method, as a new process gets created, the operating system allocates each process into available memory and is given the exact amount of memory required by the process. For example, this job tree needs a small memory, so it's allocated here. Then this job 2 needs large memory, so it is allocated here. As a process is exit, for example, this job tree is exit, they create a hole which is the region of the free memory. But if there exists a new hole which is adjacent to other hole, for example, this job 1 is exit, so this one is adjacent hole. Then this adjacent hole are merged to form one large hole here.
There are many solutions for dynamic storage allocation problem, which satisfy a request of size n from a list of free holes. They are first fit, best fit, worst fit, and circular fit. These strategies are the one most commonly used to select a free hole from the set of available holes. First fit, allocate the first hole that is big enough. Searching can start either at the beginning of the set of holes or at the location where the previous first fit search ended. We can stop searching as soon as we find a free hole that is large enough. For the best fit, allocate the smallest hole that is big enough. We must search the entire list unless the list is ordered by size. This strategy produces the smallest leftover hole. For worst fit, allocate the largest hole. Again, we must search the entire list unless it is sorted by size. This strategy produces the largest leftover hole, which may be more useful than the smaller leftover hole from a best fit approach. For circular fit, it's quite similar with first fit. It finds and allocates the first hole of memory that large enough to satisfy the request starting from the previous allocation. Simulation has shown that both first fit and best fit are better than worst fit in terms of decreasing time and storage utilization. Neither first fit nor best fit is clearly better than the other in terms of storage utilization, but first fit is generally faster.
Assalamualaikum warahmatullahi taala wabarakatuh. Saya Farah Iriani binti Rosman dan dalam video ini saya akan membentangkan tajuk fragmentation. External fragmentation exists when there is enough total memory space to satisfy a request but the available space are not contiguous. This fragmentation problem can be severe. In the worst case, we could have a block of free memory between every two processes. If all these small pieces of memory were in one big free block instead, we might be able to run several more processes. Whether we are using the first fit or best fit strategy can affect the amount of fragmentation.
Consider a multiple partition allocation scheme with a whole of 18,464 bytes. Suppose that the next process requests 18,462 bytes. If we allocate exactly the request block, we are left with a whole of 2 bytes.
The overhead to keep track of this whole will be substantially larger than the whole itself. The general approach to avoiding this problem is to break the physical memory into fixed size block and allocate memory in units based on block size. With this approach, the memory allocated to a process may be slightly larger than the request memory.
The solution to the problem of external fragmentation is compaction. The goal is to shuffle the memory contents so as to place all free memory together in one large block. Another possible solution to the external fragmentation problem is to permit the logical address space of the processes to be non-contiguous, thus allowing a process to be allocate physical memory wherever such memory is available.